Today we're going to look at using the measurements from a titration experiment to work out the concentration of the unknown solution. Whilst I'll be using the results of an acid-base titration as an example, this process is the same for any titration. I will also avoid using any extra equations, some of which can make assumptions which may not be true in all cases. The only maths equation you need is written in plain sight on the bottle of the known reagent. It's the units of concentration. Whilst you may not consider the units of concentration to be a maths equation, they are. When we say that the units of concentration are moles per litre, the per bit of that sentence can be thought of as divided by. In other words, the concentration equals the number of moles divided by the volume in litres, an equation. In fact, this is the only equation we need. Providing we have two of the three items in this equation, we can calculate the third. For example, if we have the concentration and the volume, we can calculate the number of moles. We do this by multiplying both sides of the equation by the volume. This shows that the number of moles is equal to the concentration in moles per litre multiplied by the volume in litres. Here's the example data I'm going to use for the calculations. If you want to see how the titration was carried out, I'll put a link to that video in the description. The first thing to do is to average the two titration values that are concordant. They agree within the precision of the experiment. If you have values that don't agree, don't include these values in the average. For instance, you might have performed a rough titration first just to get an idea of the values. Here we have two values that agree, so we'll average these. I really do recommend taking the time to lay out each line of calculations like this. Each line should have 5 items. First, some text explaining what is being calculated. Next, how this is calculated. For simple calculations like this, I would use text, but for more complicated calculations, I would use symbols, provided that they had been defined before they were used. Thirdly, the actual numbers used in the calculation. Fourthly, the numeric result. And finally, but very importantly, the units of the result. Like this, the reader can follow your calculations easily. Probably even more importantly, if you realise that the final answer is incorrect, you can look back and see where the error lies and then correct it. At this point, we can construct a table of information like this. Here we can see that we have more information about one of the reagents. So we'll start our calculations with this reagent, in this case the sulfuric acid. Since we have both the volume and the concentration of acid, we can calculate the number of moles used in the experiment. From this, we can infer the number of moles of sodium hydroxide by using the stoichiometry of the reaction. Once we have the number of moles of hydroxide used, since we have the volume, we can calculate the concentration. So let's start with calculating the number of moles of sulfuric acid used. As I showed earlier, we can rearrange the concentration equation so that it will give us the number of moles of acid. Now we can put in the numbers. However, the units of volume used in this equation are litres. So we must convert the volume in millilitres to litres by dividing by 1,000, the number of millilitres in a litre. Once that is done, we can calculate the result and make sure that we include the units. To infer the number of moles of base from the number of moles of acid, we need to check the overall reaction. Here it is. Here we can see that 2 molecules of sodium hydroxide react with 1 molecule of sulfuric acid. We say that the stoichiometric ratio is 2 to 1. So if we used exactly the right amount of sodium hydroxide, we'd have added twice as many molecules of sodium hydroxide as there were of sulfuric acid. Hence, there will have been twice as many moles of hydroxide as there was of the acid. We write that as the number of moles of sodium hydroxide is equal to the number of moles of sulfuric acid multiplied by the stoichiometry. In this case, that's 0.00108 times 2, which yields 0.00216 moles. This result means that we now have both of the necessary values to calculate the concentration of the sodium hydroxide. We have just calculated the number of moles used in the titration, and we have the volume of the solution that provided those moles. To get a concentration in moles per litre, we need to divide the number of moles by the volume in litres. Again, our volume is in millilitres, so we convert it to litres by dividing by 1,000. In this example, this means 0.00216 moles divided by 21.875 millilitres divided by 1,000 to convert the volume to litres. It is really important here to do the steps in the correct order. Convert the millilitres to litres first, then use that value in the calculation. If we do this correctly, we obtain a value of 0.098742 moles per litre. However, we only know the concentration of the acid to 3 significant figures, so we can only quote our final answer to a similar precision. In this case, the answer rounds to 0.0987 moles per litre. This method works for any titration, not just acid-base reactions. Sometimes the unknown will be in the conical flask, sometimes in the burette. The stoichiometric ratio won't always be 2 to 1. But you will always know both the volume and the concentration of one of the solutions. Start there, calculate the number of moles of that compound, then use the stoichiometric ratio, whatever it may be, to calculate the number of moles of the other compound. And then you will have both the volume and the number of moles to calculate the concentration. Titration calculations always involve those 3 steps.